Thevenin's theorem states that any linear circuit containing several voltages and resistances can be replaced by just one single voltage in series with a single resistance connected across the load. This is to say that any electrical circuit can be simplified into a two-terminal circuit with just a single constant voltage source in series with a resistance, noting that this can also be a complex impedance, connected as shown. Imagine that you're looking back into the circuit from the perspective of the load. All of the various resistances may as well just be one Rs, and the voltage across the terminals is just the source voltage, Vs. Let's go through the steps of getting to this equivalent circuit. First, remove the load resistor RL, or any component concerned. Secondly, find Rs, that is, the source resistance, by shorting all voltage sources or by open circuiting all the current sources. Third, find Vs, that is the source voltage, by use of the usual circuit analysis methods. Fourth and finally, find the current flowing through the load resistor RL. We'll now perform these steps on this example circuit to find its Thevenin equivalent. So first we remove the load resistor. We know it's this 40 ohm one here because we can see the terminals on either side. Next, we short out all the voltage sources to remove any internal resistance. Here, we're simulating an ideal voltage source. We then find Rs, that is the source resistance, by calculating the total resistance looking back from the terminals AB with all the voltages shorted. We can see that the two remaining resistors are in parallel. This is because the resistors lie on two separate lines that both run from A to B, representing two potential current paths. As we are looking to find the total resistance, we must then consider both paths. Recall how we calculate the resistance of circuit elements in parallel. We now find the equivalent voltage Vs. This is the voltage across the terminals and also can be considered VAB. We do this by reconnecting the two voltages back into the circuit and finding the current about the loop. Using Ohm's law and taking the 20 volt source as our reference polarity, we now use this to calculate the voltage drop across the 20 ohm resistor or the 10 ohm resistor. Now we have the source voltage Vs, as well as the source resistance Rs. This means that we can form the Thevenin equivalent circuit. Note that we've reintroduced this load resistance that we took out at the start. If we wish, we can also find the current flowing around the circuit and through the load. This is a very powerful tool to understand, but it's important to note that we haven't changed anything in terms of the way the circuit behaves. It is electrically identical to the complex circuit we had before.